design. Design. Design of steel beams. Right. So I see will send me an image in which she got the shock of her life. See what's going on here. What is this? It's nothing to panic about. But let me do justice to that thing. Right, so you were given a cross section like this, right? And you were given an eye section like this. And what was the size of this eye section? And what were the dimensions? These dimensions we can create our own. It doesn't necessarily have to be from the textbook. So let's say this is 200, and let's just make it a square, 200 by 200. Who's this late come? Mal. You are late, very late. Right. Just allow me to rejoin. Can you see my screen?
Yes, sir.
Right. So the thickness. Let's just make this thickness. So this kind of beam which I want to deal with today is called a compound beam. Right? So the concept is very much similar to what we used to cover in N5, right? And we're going to apply that concept from N5, but with a slight difference in the sense that certain information you can readily get it from the Redbook if you're given, let's say this I section is a standard section. So if this I section is a standard section, let's say you've been given an I section in parallel flanges, and that I section in parallel flanges is a, let's say it's a 254 by 146. 254 by 146 kgs by 31.3 kgs per meter I section with parallel flanges. Right. Now the question which is given here is determine the maximum. Determine the maximum UDL, which the compound section, right, can carry. So this type of if it spans, let's say 5 meters. Was it the kind of question which you were given, Lindy? Is Lindo here? Jesus, please talk to me, guys. I have other things to do.
She's here, sir, but she was having problems, so I'm not sure if she's having network problems or what. But she's in the meeting.
Alright. Okay, it's fine. I read a confirmation from you, but it's fine. So determine the maximum UDL which the compound section can carry if it spans 5 meters. So what's happening here is the question may not be phrased this way. It may be phrased in such a way that it's in sections. Right? So they may say calculate the position of the neutral axis, determine the moment of inertia, calculate the maximum moment of resistance, the maximum imposed load the beam can carry safely if the effective span is 5 meters, and the position and magnitude of the maximum shear stress. So that's how the question may be phrased. It may be phrased slightly different to what we are going to do here. Right. So what's
So I just found the question. Do you still want it?
Yeah.
I found India's question. Do you still want it?
Yes, it's fine. You can give me that information.
Figure 3 shows a compound beam consisting of a 203 by 203 by 53.5 kilonewtons per meter 8-section parallel flange steel beam supporting a 180 by 150 by 4 millimeter rectangular hollow section over a span of 6.5 meters. Assume a self-weight for the compound beam to be 125 kilonewtons per meter. The maximum bending stress must not exceed 148 MPa. The density of the structural steel is 7,860 kilonewton meters cubed. That's all. Make a neat sketch and calculate the maximum uniformly distributed loads that the structural steel connection can support.
Okay.
And then it's the question out of 20.
Right, so you can see that it's phrased differently, but the whole point is you're supposed to calculate the maximum load which can be applied to that beam. So this is how you are going to handle such a case. So you've got a beam, right? It's simply supported. And this beam has got a span of LE. And we are told that this thing has got a self-weight. Right? Then on top of this self-weight, we want to find out what is the live load which can be carried by this beam. So this is the question. What is the maximum point load, not point load, live load, which can be carried by this beam if you are given a span of, let's say, 5 meters, right? And this particular beam is a compound beam. A compound beam simply means a beam in which one section is placed on top of the other, right? So that's what we refer to as a compound beam. It's a combination of sections which make up one cross-sectional area. So for instance here, we can weld here and there. And the moment we weld here and there, then means that this thing is now behaving as one continuous member. Right? So another example of a compound beam could be an I section, but that I section which is made out of individual plates, which is not a rolled I section which you easily get from the landfill. You can create your own I section, and by creating that own I section, it's also another example of a compound beam. Right? So do you understand the concept of what's meant by a compound beam before we proceed?
Yes, sir.
Okay. So if you understand what's a compound beam, then let's now look at the two equations which are going to help you out in understanding how to tackle this situation. Right. So for beam stability, right, or for a beam to be able to carry enough strength, there's a condition which must be satisfied, and it is that condition which you're going to use to determine the maximum force which can be applied to that beam. So you must understand that there's an ultimate moment, right? Maximum applied bending moment. So this one is effective bending moment. You are familiar with MU from our calculations in building in the concrete section. Right. Then we have what we refer to as moment of resistance. Moment of resistance. So if we're talking about the moment of resistance, we're talking about the maximum bending moment which a section can provide. And for stability, the condition is the applied bending moment must be less than or equal to the moment of resistance. So that's a condition which will ensure that the compound beam which we have is going to be able to provide support to the load there. Right? So the moment you have the moment of resistance, where does this moment of resistance come from? It comes from the strength of material. It comes from the section modulus. Right. So the geometric properties which are defined by the section modulus, as well as the strength of material, which is defining the yield strength of the material, Fy. Those are the ones which make up the moment of resistance. Then the ultimate moment, where does it come from? It comes from loads, right? As applied to the structure. Right. So I'm not going to get into too much theory because we don't have a lot of time. But I want you to understand that this load, the ultimate load, is the maximum bending moment. Like the maximum bending moment is equal to things like omega LE squared over 8. Alright? So this is a situation for a case like this, where we are having a UDL and the distance between supports is that, and omega is the uniformly distributed load per meter. Right. Then MU is equal to omega LE squared over 8 plus PL over 4. If you've got a scenario like this, you've got a simply supported beam, you've got a UDL, and you've got a point load. But where is that point load acting? That point load is acting at midspan LE over 2, LE over 2. So this is the point load, this is omega. Do you see what we're talking about here? Right. So this MU is the ultimate bending moment, or is the maximum bending moment, which you obtain after having done your calculations based on the loads that are being applied to a beam. Is that clear? Guys, are you still there?
Yes, sir.
Yes, sir.
So this scenario here, MU, it depends on the situation. So for instance, I've got a point load, just a point load, like this. So that's the reaction. My MU will become PL right? E over 4. That becomes the maximum point, that becomes the maximum bending moment. So you must understand that the maximum bending moment depends on the situation. Right, so if you have a beam like the ones which were given in N5, then you have to determine the position of the maximum bending moment from first principles, like what we used to do in N5. So you then have to apply that concept, determine the position where the maximum bending moment is acting, and it is that maximum bending moment which you use as the basis for then doing your beam design. But I want to emphasize that these two scenarios are the ones which you are likely going to get in your exams, right? Where you are having a uniformly distributed load, and where you are having a point load and a uniformly distributed load. But that point load is acting at mid-span. So you are going to concentrate on these two, right? So right, let's move on to the moment of resistance. Moment of resistance. So the moment of resistance, do you remember the fundamental bending formula, which we used to say moment of resistance is equal to allowable bending stress multiplied by section modulus, ZE, where ZE is the section modulus. Right. What is section modulus? It's representing the resistance which is offered to bending by a shape. Right. So it's a geometrical property. Then what is sigma allowable? It is the strength of the material. Strength of the material. So whenever you're given a question of this nature, right, all they want you to do is to play around with this expression. How do you play around with that expression? You play around with this expression in this manner. We know that the ultimate moment can either be that or it can be that. So what it means is my ultimate moment, which is equal to omega LE squared over 8, should be less than or equal to my ultimate moment of resistance, which is equal to sigma allowable multiplied by ZE. Right? So which means if we take out that and that, which means we are looking at the situation in which omega LE squared over 8, right, is less than or equal to sigma allowable multiplied by ZE. Right, so I want you to understand this concept. Right? So that's the first formula. Right. So we're going to call this number 1. So this applies to a situation in which the loading is like this. It's a UDL which is acting right throughout. That's when you use that formula. So the second scenario, your ultimate moment MU is equal to omega LE squared over 8 plus PL over 4, right? Which must be less than or equal to the moment of resistance, which is still sigma allowable multiplied by ZE, which is the section modulus. So omega LE squared over 8 plus PLE over 4 should be less than or equal to sigma allowable, right, multiplied by ZE. Right. number 2. Is it making sense? What we are discussing right now.
Yes, sir, it makes sense.
Right. So those are the 2 scenarios. So what we are simply doing here is we are equating the ability of a beam to resist bending to the applied bending moment. So that must always be balanced there. You must always have a situation in which the ability of a beam to resist bending is greater than the load which is applied there. So that's what you must always understand there. So depending on the situation which you have, you are either using option 1 or you are using option 2. That's what you should do. But now, what does this question requires us to do? If you are given this information, what do we do with this information here? That's the question which you may be having. What do we do with this information? How is it relevant? Right? The relevance of this information is that it allows us to calculate ZE, the section modulus, from first principle. So if you have the information about the cross-sectional area, it allows you to then determine the section modulus, because that's information which is given. Why is this section modulus important? Because you are going to use it here. You're going to use it here or the other formula. So that's the reason why that information is given there. Alright, so information about the allowable yield stress of the material, that information will be given. You'll be told what type of material is being used and all that. So because of that information, you should be able to then determine the maximum load which is there. Right. So let's move on to the question. And now look at how we're supposed to go about it. So let me take this. Right. So what are we going to do with this information? So the first thing which we are going to do is right. So determine the position of the neutral axis. So determine the position What is the relevance of calculating the position of the neutral axis? It is because we will then use this position of the neutral axis to calculate the second moment of area. Then once we have determined the second moment of area, we will be in a position where we can then determine the section modulus. So we've got a compound beam. We don't know whether the neutral axis is going to be here from your N5. Remember that calculation of y bar. Or we don't know if it's going to be there. We don't know yet. So do you remember what we used to do in N5? So we used to draw a table, which would then say shape, then we have area, then we had y, then we had ay, right? Then from there we had h, h squared, and I neutral axis. Do you remember that table? So let's go there. Let's say shape, right? Area, y, ay, h, a, h squared, then I neutral axis. Right. We used to calculate this thing like this. Right. We've got shape 1 and we've got shape 2. And we're going to get the total. So shape 1 is the I section. And this I section, what size are we dealing with? We are dealing with the 254, 146, 31.3. 254 universal beam 31.3. Right. Then the other section is a square hollow section, and I've said this is 200 by 200, 200, 200, and let's say the thickness is 6 millimeters. Right. So for calculating the area of the 254 U beam 31.3, we don't need to calculate from first principles. Why do I say that? It is because this information you can get directly from the Red Book. So from the Red Book, you just go into the Red Book and you select the area of the 254 universal beam. So let's look at what is the area from the Red Book. So that universal beam which we have, what's the area? Let's check from the Red Book. Are you guys checking? Assist me, I'm looking for my Red Book here.
Can you please repeat, sir?
Right, so we are looking for the area of a 2, is it a 245? Let me see. 254, not a 245, I made a mistake here. So, if we go into the Red Book, we are looking for the area of a 254 I section and parallel flanges, and it's a 254 by 146, and it weighs 31.3 kgs per meter. So what is the area?
So I get 3.992.
Okay, 3.992. So
It's
this is 3,992 square millimeters. Right. So the units of measurement, you know, we put here square millimeters. So 3,992. So you don't have to go and calculate the area of that flange, then you add for that web, then you add for that flange. No, because you are already getting it from the Red Book, so there's no need for you to do that calculation. So that area we have now. So here we have to have totals. Right, for this one, the area is the area of the shaded section. Right? So this is going to be 200 squared minus. Now, if I subtract 6 times 2, which is 12 millimeters from 200, what do I get? I get 188. Is that correct? Guys, what appears if we are lost? We've got a rectangle like this. It is 6 millimeters thick, this side, 6 millimeters thick, that side. So I want to know what is the dimension of this internal rectangle, and I've got the dimension of this external square, and that value is 200. So if I say 200 minus 12 millimeters, what do we get?
188 squared.
So this is going to be 188 squared. Right. So if I subtract 200 squared minus 188 squared, it gives us the area of the rectangular square section. What do we get here?
So I've got 4656.
4656, like this. Alright,
Yes.
that's fine. So what's the total? So this is going to be 8, 9 plus 5, 14, 4 carry 1, 10, 16, 6 carry 1. That's 8,648 square millimeters. Do we agree?
Yes, sir.
Okay. Alright, is there anyone who still having connectivity issues? You guys have gone rusty. Just these few days. And no longer want to talk to me. It's fine. It's only 3 days. Right, so let's now look at the value of y. It is the distance from the reference point, which is usually the bottom of the compound section, to the centroid of that particular area in question. So what we are doing here is we've got a compound section like this. Right. So from the bottom, from our reference there, we want to find out to the centroid of that I section what is the value of y1, and we also want to find out from this reference the center of that square or low section, what is this distance y2, right? But if you look at this section, do you see that it's symmetrical? It's a symmetrical section, which means that the position of the centroid for the I section is exactly at mid-height. If this is the height from there to there, if this is h, the height of the 254 by 146 section, it means y1 will be equal to h over 2. Why I'm saying it's h over 2? Because it is symmetrical. So the centroid will be right at the center of that shape. Is that clear?
Yes, sir.
Right. So if it's going to be at the center of that shape, what it means is we have to go into the red book and select the value of the height and divide that by 2. Right. So if you go for h for that section, 254, 146, 31.3 kgs, it's 251.5 millimeters. Am I correct? I'm saying
Yes,
the height
sir.
is 251.5, but we are dividing this by 2. So what does it give us?
So it's 125.75.
125.75 millimeters. So that's the distance from the base to the centroid of this section. It's much easier. Now, let's now look at how do we build up the value of y. So when it comes to y, how do we build up this value? Y2 is going to be equal to h. Why am I saying h? Because the distance from the base goes to the bottom of that square or section. So that overall distance is h. Plus, we also want that small distance. But because this is a square, so we also know that the height of this square h is going to be h. So to the centroid of that square is going to be h over 2. Is that clear? So y2 is going to be h1 plus h over 2. Is it making sense? To get the overall distance of y2. But we do know that h1 is equal to how much? Was there a question?
No, sir. So
So what's the value of h1?
So it's 100.
h1 is
H1. So that's 251.5.
that's 251.5 plus, right? What is the value of h? From there to there, you can see that we are looking at 200. So it's going to be 200 divided by 2, which then gives you a total of how much? 351.5 millimeters. Is that correct?
Yes, sir, it's correct.
351.5. So I come and write 351.5 millimeters. And you know that in this section we don't need any totals. So the next section is straightforward. So this is going to be millimeters to the power 3 cubic millimeters. We are multiplying that times that times that. What does it give us? 3992 times 125.75. You don't even need to write this information here. You can do that calculation and just write the final answer.
So it's 501,900.
Express it as maybe 10 to the power 3.
501.994.
501.994. Right. Try to work to 3 decimal places. So this is going to be 501.994 and everything is going to be times 10 to the power 3. Right. So 4656 times 351.5.
So that's 1,636.
1,600.
36.584.
584 times 10 to the power 3. What's the total? 501.994 plus 1636.584. Why are we having one person contributing, guys? Let's have everyone contributing to this thing.
2,938.578.
2,
138.578.
578, like this. Okay. So with this information, then we can calculate position of the neutral axis y bar is equal to sum of a y over sum of area, which is 2138.578 divided by 8648. What does it give us?
It's 247.292.
Yeah? I didn't quite get that.
247.292.
2 what?
47.
247.292,
292.
like this.
Yes, sir.
Okay. So that 247.292, that's your position of the neutral axis. Right? So your neutral axis is somewhere there. Right? So that's your y bar. Right, so once you get that y bar, you now want to find the value of h. But h is equal to modulus of y bar minus y, or you can say modulus of y minus y bar. It doesn't matter. We just want the difference. You book that value as a positive value, then we are done. So you're now saying 247.292 minus 125.75 to get h for here. It's going to be 247.292 minus 125.75. What's the answer?
So I get 121.542.
542. Right, so remember, this is in millimeters. Right, so let's do the same thing. 351.5 minus 247.292.
So I get 104.208.
104.208. Is everyone getting these values? Because we have to.
Yes, sir.
Okay, it's fine. So if we're getting the same values, then that's fine. So your total here, we don't need any total. Agreed. So there's no total for this section. There's no total for that section. Right, so let's now calculate a h squared. So this h squared, we are now saying this value of a, this value of a times the square of that value. Most people make a mistake here. They just multiply these two and forget to multiply by the square of 121.542. So please make sure that you are raising 121.542 to the power 2. Then you multiply by 3992. Right, so let's get the value. And I want you to express that value times 10 to the power 6. Because here you are going to get millimeters to the power 4. So the units of measurement will be millimeters to the power 4. And here it's also going to be millimeters to the power 4. And we are going to raise everything 10 to the power 6.
So I got 58.972.
Huh?
58.972.
58.972 times 10 to the power 6.
Yes, sir.
Okay. The next person, give us the value of 104.208 squared multiplied by 4656.
It's 50.561.
50.561. Like this.
Yes.
Okay, so let's add the 2. We are adding that plus that. What answer do we get?
So I get
19.53.
Yeah?
109.533.
109.533. squared. Fine. So let's do for I neutral axis. So here you have to be careful. So you see your I section is in that compound section like this. You see that? The I section is upright like this. So we're going to use the IXX values. If your I section is placed like this, then you use Y values. You get it? So from the red book, you are going to select IXX because it is placed upright like this. So let's go in the red book and look for the second moment of area about the x-axis for a 254 146 by 33.1. I'm getting a value of 44.28 times 10 to the power minus 6 meters to the power 4. That's what I'm getting. Are you getting something different?
So I'm getting the same.
Right. So we need to convert these to millimeters to the power 4. You see the values in your red book are given in meters to the power 4. We want it to be millimeters to the power 4. Okay. So just give me a minute. I just need to check how. I just need to confirm with something. What section is that? A 254? What? 254 146 by 31. Right. To convert it to millimeters to the power 4 is exactly the same value. Right. So this is the same as 44.28 times 10 to the power minus, sorry, not minus 6, 10 to the power 6 millimeters to the power 4. So if you want to convert this to millimeters to the power 4, you are just making this one positive. You get it? You're just making the value which you are getting from the red book, you are making it positive. So here, we're going to come and write 44.28. 44.28. And this is times 10 to the power 6. Right? Millimeters to the power 4. We are good to go. Then, how do we get the second moment of area for a square hollow section? How do we do that? How do we calculate that? Anyone?
BH cubed over 12.
Yes, that is half the answer.
So must we not do that exact formula but do it twice and minus them from each other? Because it's
Yes, you are right. So this is B. B is always the width. This one is H, right? Or some will call it D. Right? So it doesn't really matter which notation is used. Then this one, the small letter one, call it B, and this one call it H. Right? So the second moment of area about the x-axis, x will be equal to b h cubed over 12 minus b h cubed over 12. Please don't forget that this is raised to the power 3. This is raised to the power 3. It's very easy to square that thing when it's actually raised to the power 3. If you square it, then you're in trouble. Right. So we know that B is 200 and H is 200. So this is going to be 200 times 200 to the power 3 divided by 12 minus 188 to the power 4 divided by 12. It's the same because I was just going to say 188 times this, just to it in that manner, times 188 to the power 4 divided by 12. What answer do we get? No, this one is not to the power 4, so this then becomes to the power 3. What answer do we get?
So I get 29.233.
Right. Times 10 to the power 6 millimeters to the power 4. So 29.233 is what you're going to write here. 29.233. So let's add these two. 44.28 plus 29.233.
So that's 73.513.
73.513.
513.
Right. So therefore, I total will be equal to sum of I neutral axis plus sum of a h squared. The parallel axis theorem. So which means I neutral axis is that value, 73.513 plus AH squared is 109.533. 109.533. What answer do we get?
So I get 183.0.
One
183.
point
046.
046 times 10 to the power 6 millimeters to the power 4. So that is the second moment of area about the neutral axis for the compound shape. So that compound shape, which looks like this, and having a neutral axis somewhere there, which is our y bar, is having a second moment. This whole thing has got a second moment of area of 183.046. Is that clear?
Yes, sir. Yes,
Yes.
sir.
Right. Now, so once you have determined the second moment of area, or what they call the moment of inertia, so moment of inertia, or second moment of area. So it's the same thing. So it's just referring to the same thing. So once you get the value of the second moment of area, then you can calculate the section modulus. So Z is equal to I total divided by Y bar. Z will be equal to the second moment of area divided by Y bar. So this will be equal to second moment of area, which is 183.046, 183.046 times 10 to the power 6, right? Millimeters to the power 4 divided by Y bar. What did we get as our value of Y bar? 200 and what? We got this value as 247.292. 247.292. Right. What are we going to get?
So about 0.7.
Do like this. Write that expression as it is. 183.046 times 10 to the power 6 divided by 247.272. We'll cancel out these ones later. But write it as it is. Calculate that thing as it is shown on the screen.
So if I do as it is, and it's 740,201.
But make it times 10 to the power 3.
So then it's 740.202.
Times 10 to the power 3 millimeters to the power 3. Right. Why millimeters to the power 3? Because millimeters to the power 4 divided by millimeters. So this will cancel out, then you're going to get millimeters to the power 3. Alternatively, if you want to express it as cubic meters, then it means you then have to say 740.202 times 10 to the power 3 times 10 to the power minus 9, because millimeters to the power 3 is 10 to the power minus 3 to the power 3, like this, which becomes 10 to the power minus 9. So it then becomes 740.202 times 10 to the power minus 6 meters to the power 3. Right, so if you want to express it in meters to the power 3, then you know this is how you have to do it. So it just depends on how you want to express it. But the section modulus for that thing is this value. So that's the value which we have obtained there for the section modulus. Either you express it this way or you express it this way. It's still the correct value. So once you have determined the section modulus, right, we can then come back to this expression. We are coming back to that expression now. Get it? But remember, what is the objective of our calculation? The objective is to calculate the maximum uniformly distributed load which can be carried by the beam. You get it? So we want to find out what is the maximum load which is uniformly distributed, which can be carried by the beam, right? But we've already obtained ZE. We need to determine what is the allowable bending stress for the material. Then we are told that the span is 5 meters. Therefore means the only unknown becomes the uniformly distributed load. Okay. So now let's go to the next step. Let's say determine the we want to determine the design stress. Determine the design stress. So remember, the standard which we are referring to is SA BS0162 Part 3. Right. So this standard then gives us the values of allowable bending stress. Right. Allowable bending stress, and it is annotated PB. So PB is equal to, so where do we get that information from? So let's go to page 94 of your textbook. Do you have your textbooks with you? Okay, so if you go to page 94 in your textbooks, clause 7.1.1, 7.1.1, it reads allowable stress. The maximum bending stress at any point in a member calculated on the basis of the effective section as defined in 7.3.1 shall not exceed the appropriate value of PMC or PMT. So sorry, it's not PM, it's not PB, it's PMT. PMT. In column 4 of table 2. So table 2 is saying rope sections and compound sections consisting of rope sections. Right? If you are using grade 43 steel and its thickness is less than 40 millimeters, the allowable bending stress is 165 megapascals. Please make a correction to that table. Right? Because if you look at that table, T is given as less than or equal to 40, then they write T is less than or equal to 40 again. So please note that the bottom one must be changed to greater than 40. So when you go to column 3, right, so there's column 3, then there's column 4, right? And there is column 2, which is still grade. And here you have grade 43, then you have 300W, right? Then you go to the next section, which is talking about a different type of structural sections. Then you have grade 43, 300W, grade 43, 300W. So each time we then get to T less than or equal to 40, the other one T is greater than 40, where T is referring to the thickness of the members, right? Thickness of the members. So please make sure that you go and make that correction in that table. So let's deal with grade 43 because that's the one with a lot of tables which are referred to here. So if you're dealing with grade 43 steel, and we know that the thickness is less than 40 millimeters, there is no hot rolled structural steel section with a thickness greater than 40. So most of them, they have a thickness which is less than 40. So we're going to be using that option, T less than or equal to 40. So for grade 43, rope sections and compound members consisting of rope sections, the maximum allowable bending stress, PMT or PMC, will be equal to 165 megapascals. Right. So that 165 mega, I just want to find out because I'm not able to share my webcam with you guys. So just have to find out if you manage to get to the right table, if what I'm explaining is something which you can follow.
Yes, sir. That's our table.
Okay. Is everyone able to follow?
Yes.
Okay, it's fine. So that's sorted. So PMT is going to be 165 megapascals. Right. So after I've determined the design stress, which is coming from 7.1.1 table 2, our PMT is 165 megapascals. So the next thing is we can determine the moment of resistance of the compound section. The moment of resistance of the compound section is MR. So we know that MR is equal to allowable stress, which is PMT. Please note that the standard refers to allowable stress, that one, which I'm saying allowable stress, as PMT. So PMT multiplied by Z. So this is going to be equal to 165 times 10 to the power 6 multiplied by a Z of how much? Right, so if you look at this Z, it's 740.202 times 10 to the power minus 6. 740.202 times 10 to the power minus 6. And this is meters to the power 3. So this then gives us the value of how much? This one will cancel out with this one. So you can express this as, you could have calculated this thing directly as 165 multiplied by 740.202. Then you get your answer in kilo Newton meters. You get your answer in kilo Newton meters.
So, I've got 122,000.
Yeah, make it times 10 to the power 3.
Then it's 122.1.
Which is equal to
122.133.
133 kilonewton meters. So the maximum bending moment which can be resisted by that compound beam is 122.133 kilonewton meters. Is it making sense? So the maximum bending moment which that compound section, which we've just determined, this compound section, here, it can resist a maximum of 122 kilonewton meters. That is what it is capable of resisting. Anything greater than 122 kilonewton meters, then this section will fail. Right? This section will fail if we apply anything which is now greater than 122 kilonewton meters. Does this make sense? So this is the resistance which it can offer. Anything beyond that, then this thing will break. 122.133 kilonewton meters. Right. So from here, we can then determine now the maximum. From here, we can then determine the maximum load. Right? So the maximum total load, which can be the maximum total load, which can be carried by the beam. So from here, determine this one is omega. And going back to our formula there, right? Going back to our formula, this value of omega is what we now want to calculate. The moment of resistance we have obtained by multiplying allowable stress by ZE, right? So from there, we can then go and determine that value. So we know that omega LE squared over 8 should be less than or equal to, right, 122. PMT multiplied by Z, right? Therefore, omega will be equal to 8 PMT Z divided by LE squared. So it must be less than or equal to that. Right. So this must be less than or equal to 8 times 122.133 times 10 to the power 3, because PMT times Z is equal to that value divided by the maximum value there. Right? So the maximum value there will be how much? The maximum value there will be not the maximum value, the value of the span. Remember, LE is your span. What span are we dealing with, by the way? We are dealing with 5 meters. Right. Determine the maximum UDL which the compound section can carry if it spans 5 meters. So our LE is 5 meters. So we then go here and we then divide it by 5 squared. So what answer do we get? 8 times 122.133 times 10 to the power 3 divided by 25.
So I get 39,082.56.
Yeah, make it because load is expressed in kilonewtons per meter.
So then it's 39.08.
39.083 omega is equal to 39.083 kilonewtons per meter. Right, so this is going to be 39.083 kilonewtons per meter. Right. So that is the maximum UDL which we can place on top of that beam. So that compound beam, which is like this, right? This UDL, which we can place there, is a total of omega, which is 39.089 kilonewtons per meter. If that beam is spanning how much? LE is equal to 5 meters. But I want you to understand something. Right? I want you to understand something. And the one thing which I want you to understand is that this omega is in two parts. Get it? So this omega refers to the self weight plus imposed or live load. Get it? So that omega is equal to GK plus QK. So this is GK. This is QK. making sense?
Yes, sir.
So we are saying the self-weight of the beam plus the imposed load must not exceed 39.09 kilonewtons per meter. Right? It mustn't exceed 39.09 kilonewtons per meter. Otherwise, if it does exceed 39.09, then we've got a problem. So in order for us to ascertain the maximum live load which can be carried, we need to determine, but how much is the self-weight? So therefore, we know that 39.083 kilonewtons per meter is equal to GK plus QK. Therefore, the maximum load QK, imposed load, will be equal to omega minus GK. But how can we determine GK? But GK can be obtained as follows. Alright, so if you're talking about GK, what you can simply do is you can determine the self-weight. Right? You can determine the self-weight from where? Number one, from the Red Book. And number two, by calculation. So we want to know the self-weight of that compound beam. Yeah? We want to know the self-weight of that beam. And what is the self-weight of this I section? So the self-weight of the I section, we can get it straight from Red Book, because this one is a standard high profile. So what can we do? We go to a 254 by 146. If you look at the first column, where it gives you dimensions and properties, this thing weighs 31.3 kgs per meter. Right? Weighs 31.3 kgs per meter. Right? And what about this one? How much does it weigh? We don't have the standard 200 by 200 by 6. Like we don't. From the tables, we don't have that standard section. So we know that mass is equal to density times volume, right? But what is volume? Volume is equal to area times length. But we want to find out the mass per meter of this cross-sectional area. So our L is going to be 1 meter. So if I multiply the density of steel multiplied by the cross-sectional area of this hollow section, I can then determine the mass per meter. Right. So this is going to be 0.2 squared. Right. Why am I saying 0.2? I just want to convert it to square meters. So this is 200. This is 200. And we say this one is 188. So to convert this to meters, this is going to be 0.2. So if I say 0.2 times 0.2, that's 0.2 squared minus 0.188 squared. It's going to give me the area, cross-sectional area of, it's going to give me the cross-sectional area of this section. Are we together?
Yes, sir.
So it's giving us this cross-sectional area. Then we then multiply by the density of steel. So the density of steel is 7,850 kgs per cubic meter. Right. So our mass per meter will be equal to 7,850 multiplied by 0.2 squared minus 0.188 squared. What do we get? How many kgs per meter is that?
So I get 36.
30?
36.549.
549 kilograms per meter. So therefore GK is equal to 36 point what? 36.549 plus, we know the self weight of this one is 31.331. 31.331, is that correct? 31.3, sorry, 31.3. Right? But these are kgs, so we need to convert them to kilonewtons. So this is going to be multiplied by 9.81 divided by 1,000. Right. So what can we get? What then do we get? We then get an answer of what?
So I get 665.
Yeah?
So I get 665.599.
No. If we say 36.54 plus 31.3 times 9.81 divided by 1,000, you can't get that. 0.668. Like
666.
666. I'm scared now if I do of 666. Like this.
Yes, sir.
Kilonewtons per meter. So the self weight of that thing is 0.666 kilonewtons per meter. Right? So what we can then do is to determine the live load. We then subtract total load from self weight. So therefore QK will be equal to what is the value of omega? What did we get as omega? 39 point what? 39.083. 39.083 minus 0.666. And what does it give you?
$38.417.
38.417 kilonewtons. So that's the maximum live load which you can put on that beam per meter, so that the beam does not break. Right. Did we all understand how we got to that point?
Yes, sir.
Or we need to you need to revise it, of course. You need to revise and see how you can get to that point. So if you look at what I've done there, I haven't taken into account partial factors and all that. So if you want to be really accurate about it, you can then divide the values by partial factors. You get it? That 1.6 and that 1.2, so that you see the unfactored. So the assumption which you can make here is these are factored loads, right? You can assume that maybe this is going to be a factored load. Although that assumption may not be valid because we did not apply a partial factor here of 1.2. Right? We've just taken the self-weight directly and we've just applied it there. So if you want to be very specific and very accurate, you then have to determine the unfactored loads, right, which you can then apply there, so that you know that whatever calculation you do, the value which you apply is a value before you apply partial factors, and it's a smaller value. All right. So I am going to give you a number of links, right, to certain resources, right? And those resources will deal with this concept together with normal steel beam design and other materials. So let me see. Okay. So before we close off this section, is there anyone with a question?